All right, let's start. Okay, so we last time, at the end of our class, we discussed about something called the ADA in adaptive instance normalization. So I didn't explain it in detail, but this slide is describing the main idea about it. Okay, so so once we have this kind of an encoder network, which is our which is giving us the some activation map, and then per channel. Okay, suppose we have a 4x4 as a spatial resolution, and maybe 256 channels, and then for each channels we have 16 different pixels or activation values, right? And then those values will be normalized so that normalized using their own mean and the variance, so that their mean value becomes 0 and the variance becomes 1, which is just like the first step of a batch normalization. Okay, so we first by using its own mean and the variance, we basically make their mean as a 0 and the variance as 1 for each channel. I mean 16 different values within each channel, right? So we do the same thing on the second channel and so on. Okay, and then we scale and shift so that the mean value is this new given value, and then the variance or the standard deviation becomes this value. And where are these values are coming from? So those values are given from the style image. Okay, some style image, and then their own encoder like ES, and then from here, if we have a 256 different channels for this encoder output of our content image or target image. Okay, and then so here at the end of the output of this style encoder, we will have 256 by 2 numbers as a real value that indicates each channel's mean and the variance. Okay, so those gamma and the beta is given by our own network. Okay, so that encodes this given style image. Okay, so this is the kind of idea of instance normalization, and adaptive instance normalization, or this conditional kind of instance normalization is the meaning of it is that we obtain those values of gamma and beta based on the style image that we are given. Okay, so for the role of this network for this style encoder part is to give us the target or this new mean and the variance value for our target image to impose these statistics too. Okay, so that's it for chapter 12, and then we will move on to this last chapter of generative models. So there are so many video lectures or tutorials that you can use to study this topic. Okay, so I'll quickly go through the contents that I prepared. So okay, for the generative network, it can given this only the sketch or outline of an image, it can generate this realistic or colorized image, although the quality of it is not that good because it's one of the oldest model that were proposed a few years back. And then those images are all synthetically generated images by our model. And also it can be used for this application of a super resolution. So sometimes it's called SISR, which means single image super resolution using some generative model. So in this case, if we have some small images like 256 by 256, and then we can make the resolution bigger while maintaining the realistic kind of quality of our image. So that is one of the representative application of this generative models. And then also this is called an in-painting, where we just remove some part of an image, and then we have to reconstruct this part. Okay. So this is called the in-painting. Okay, so let's get back to some of the common or kind of familiar model to us, which is called the discriminative model, which is just doing the classification or regression. So in that case, so the setting is like, so the given information is composed of many pixel values. So for example, if we have this image as an input, and then we have so many numbers, right? And then at the end, if it is classifying whether the given image is a man or a woman, and then the final output can be viewed as just a single binary value, whether it is a 1 or 0, or if it is a multi-class classification, and then if we have maybe 10 classes, and then we will generate one hop vector that has the 10-dimensional kind of output, or it can be represented as a single integer that ranges from maybe 1 through 10, right? So it's like just choosing the most likely one among this limited number of possibilities, right? Among the 2 possibilities or 10 possibilities, right? So it's like the process is kind of reducing or decreasing a lot of, many number of information that we are given. So we are given this many number of pixel values, and then at the end we want to obtain just a single integer value, whether it's a binary or just some integer values, right? So in this case it is called the generative discriminative model, but in the case of generative model we are kind of reversing the input and output. Okay, so we just give whether it should be a man or women, and then given that as an input, our generative model should be able to generate all these pixel values that fills up this many number of like arrays. Okay, so that is the generative model, because it is basically generating some input or some particular type of data. So if it is an image type, and then it should generate the proper pixel values that can fill up each of our position and also each of our channels, right? And then if it is a text, for example, like given the question of how are you doing, and then I should be able to generate the text type of data, which can be like okay, I'm doing good, or I'm doing well. Okay, so that is composed of a sequence of a particular keywords out of so many possibilities, right? So if we think of the number of possible words that we can generate, and then there could be so many words. Which is all the possible keywords contained in our kind of English or Korean dictionaries. Okay, and then the task is to choose the proper keyword out of so many possibilities and with the proper sequence, right? At the first position or the first time step, we should be able to generate the keyword corresponding to I, and then am and doing and well or fine and so on, right? So it can be viewed as much difficult task than this discriminative model. Okay, so this generative model can be viewed as it's closely related to the machine learning problem called density estimation. So density estimation is density estimation. So density estimation is related to the task of outlier detection or anomaly detection. So if you studied the topic of this anomaly detection, and then see. Suppose we are given a particular feature vector of our data item, and then suppose we collected a 100 persons height and weight vector, and so this is a height and this is weight, for example. Okay, and then for each point or each person will be represented as a single point, right? So given this set of the data items that are represented as a particular feature vectors, and then the density estimation is the problem of like estimating or the predicting. The density estimate takes an input of an arbitrary feature vector. For example, these are particular data items that we collected, okay? And then, let's consider this particular person. Although, given this 100 persons data, we didn't observe this particular combination of or this particular feature vectors. So this can be this 173 centimeter and maybe 78 kilogram. Okay, so suppose we didn't observe this particular feature vector out of 100 persons feature vector that we collected. Okay, so in that case, the question is how likely can we observe this particular person in real world or given our data. Okay, so and then the potential answer could be like, okay, the probability of observing this particular person is maybe 80%. Okay, but suppose let's think of this person where it has a really small height, maybe 145, and then really high large weight or high weights, and then maybe 105 kilogram. Okay, so it will be really unlikely to observe this particular person, right? So in this case, our density estimation model should be able to answer the probability of observing this kind of person is only like 3% in reality or based on our data. Okay, so this is the problem of estimating the density or the likelihood, or the density is just indicating the probability. Okay, so probability density in the continuous domain. So the density estimation is telling us this likelihood of a given arbitrary feature vector. Okay, and then that density estimation model will be trained based on our given data. Okay, so in this case, the intuition is like, okay, so given this topology or this distribution or this kind of a scatter plot of our data, and then we can roughly see that, we can roughly think that, okay, in the center of our data instances, and then it will have a high chance of observing this particular point or this particular point. Okay, but somewhere over here, and those will have a low chance or low probability of observing that particular data. But still, all these data can be viewed as unseen data. So they are still unseen data because this particular point and those are all, they are not included in our data, right? So in that sense, from the machine learning perspective, those data can be viewed as unseen data. Okay, so once, so this density estimation model can be viewed as like this. So X is any given or arbitrary feature vector of our data item, right? And then this P of an X should be able to give you the probability of observing that particular data, right? And that is the final density estimation model that we can train based on our data. And then from here, once we obtained this density estimation models, for example, if this is, in particular, this is actually a normal distribution. Although we do not know in advance, we are not sure whether our data is following the normal distribution or not. But let's assume that this data distribution is following the normal distribution, and then this normal distribution is specified with this mean and variance, for example, or maybe 170 and maybe 10 squared. Okay, so once we modeled our density that can give us the probability of an arbitrary feature vector. Okay, and then here, so far the setting is still like we have to give an particular input vector, right? But what if, once we know already this density model, and then, what if we just randomly generate a particular feature vector that is sampled from this particular density model? Okay, so that is kind of main idea of this generative model. So generative model, whether it is it has an explicit form or implicit form, and then it commonly, the common thing of most of these generative model is to learn this particular density model, and then when we ask this density model to generate a random sample, okay, and then it will generate a kind of a random sample just sampled from this particular or this density model or this particular density equation or expression. Okay. Okay, so in the case of a density estimation, which first learns this particular density, and then let's see. If we think of this a simple example of this rolling a dice, and then this dice was like carefully manipulated, carefully manipulated, so that it has the probability, zero probability to generate like the dice value of 4, but it has the probability of like 1/3 for the value of 6. Okay, so we can think of this as specially crafted dice that we have. Okay, but we do not know this table in advance. Okay, we do not know this table in advance, but from those data that we obtained, like 100 persons that we collected in terms of their heights and weights. Okay, so in this case, we can maybe collect 100 different samples by just rolling this particular dice. Okay, and then we can think of some kind of an histogram, right? So how many ones did we observe out of 100, or how about 2 or 3, 4, 5, and 6? Okay, and then it may have some errors like this, but it will not have any 5 values, right? And then maybe like this, right? So given this empirical kind of observation of just counting how many occurrences of a particular value that we see, okay, and then we can kind of estimate this kind of true or ground truth probability table based on this empirical kind of a histogram. So although that is really, really simple, but that can be viewed as one simple way of doing the density estimation. Okay, and then suppose, okay, so we kind of estimate or we approximate this unknown but ground truth probability table by using this empirical table based on our observed data. Okay, and then from there we can generate a particular data item by just following this probability distribution, right? And then although that is really a simple kind of process, but at that point we now have a capability of generating a new data. Okay, so instead of just having to collect like real data or really kind of existing data, which can be kind of costly, once we modeled this kind of density, although they may have some approximation or some inaccurate part, but once having it, okay, we can just synthetically generate those data with the unlimited number. Okay, so we can infinitely generate those data, right? So that is the main idea of the generative model. Any questions so far? So okay, so now the problem that we deal with is not as simple as this case, right? So in this particular case, our observation is composed of a scalar value, right? And also that scalar value is a discrete value. So in that case, the the density estimation process is quite simple. But now, if we consider this particular image of like a 64 by 64 by 3, and then we can view it as really long high dimensional vector of having the dimension of like this number, right? And then we can think of their high dimensional probability density function, right? And then suppose we are given 100 different facial images, okay? And then in this really high dimensional space, there may have, there would exist some particular region where many data items are densely located, or some regions where there is no data at all, almost, right? So in that case, we can roughly think of like, okay, so this particular region is like the kind of a high probability region that can generate the particular the data corresponding to that region, or some other areas corresponding to those unlikely region where the data can be generated. Okay, so yeah, inherently or fundamentally, so if you have this picture in mind, and then it is already like a two-dimensional example, right, which is like multi-dimensional. So we have no problem of extending this kind of idea into much higher dimensional space. Okay, so from the perspective of this facial images, suppose we have 100 different facial images, and then suppose the original kind of distribution like this, although it is not known, but we can we can assume that there exists some ground truth probability density, okay, where our data was generated from. Okay, so this is our ground truth but unknown probability density. But here in this case, this is just represented as a scalar value. Okay, so although we deal with this really high dimensional vector space, but let's imagine that it is just a scalar. Okay, but that scalar is like a continuous value, right? And that way we obtain this kind of a continuous distribution. Okay, and then in this case we have some relatively dense region that can generate our data with a high probability. Okay, in this case it can it can correspond to those man images with the glass. Okay, and then maybe some other dense regions that where the data can be generated like relatively frequently, and then it may correspond to the women with the black hair, and then maybe women with the blonde hair, right? So from this example, at least if this probability density is true, and then what it means is we may see we may see this women with the blonde hair with a higher probability compared to the women with the black hair, and also man with the glasses, and the probability of seeing that particular person is smaller than the probability of observing the women with the black hair. Whether it is a kind of, correct or not, but at least if we think of this particular example, and then this is telling us such kind of intuition to us, right? Okay, so in this case, for this region, okay, where we didn't see our real data in the nearby region, okay, or the neighbor region, and then the corresponding like 64 by 64 by 3 kind of vector, okay, in that case that corresponding image will not be likely to be observed in reality or in the real world. Okay, so in that case, so this doesn't look real. So, but this particular image will have a particular feature vector having this particular dimension. Okay, so that way, this image has a low kind of probability to observe in reality. Okay, so So the density estimation is like, so this, we can assume that there exists the ground truth probability distribution, although that is not known in advance, right? But based on our limited number of our data, we want to approximate this unknown but ground truth probability by using our data items, right? And so suppose given maybe 100 facial images, and then our particular density estimation model gave us this particular density. So in this case, the red one is like estimated density model based on our model and also our data. Okay, so if they are close enough, and then we did a good job of estimating the true density by using this approximate one, right? Okay, but if our density model was like really having a different density patterns with the ground truth, and then it may be viewed as like a poorly estimated model. Okay, so again, once we modeled this density, and then we can just randomly sample from that density model, okay, to create unlimited number of synthetically generated facial images in this particular example. Okay, then there are many different density models from the kind of pedagogic kind of categories, but I'm not gonna discuss the details about it. Although it will be quite interesting, but I'm gonna skip this part. And then we have some explicit versus implicit density model, but I'm gonna give you just a few examples of this explicit density model. Okay, so there is a model called pixel RNN and also this pixel CNN. Okay, so in this case, so pixel RNN is LSTM based generative model. Okay, so the direction can be like the direction can be formed in a different manner, but let's just think of the generative model or the sequence of generating each of our pixels in our image of having the size of 64 by 64 by maybe 3, and then suppose we generate this first the pixel at the left top region or position, and then once this pixel value is generated and fixed as a particular value, okay, and then it will determine the probability of generating those two other pixels nearby or in a neighborhood. Okay, so the main intuition is something like this. So given kind of facial images, okay, in the facial images. So facial image, you can think of like this kind of density in terms of this really less likely region or highly likely region is like, so given our facial images, okay, so suppose we took the photos of facial images with the black background, okay, black background. We need a hair, but okay, so let's just consider the bold, just the bold faces, and then these will be all blacks, okay, so these will be blacks. So suppose we observed like pink or like a skin color, okay, skin color at this particular position, okay, and then it indicates that, okay, so from here following this kind of direction to the right and to the bottom, and then once we observed some skin color pixel value, And then we can also think of, based on that, that kind of clue or observation, we can think of like this pixel will not be likely to be a black pixel, right? Because it is indicating, okay, so we start our facial region, right? And then moving to the right and then the bottom. And then, it will not likely that the facial region is ending just with the single pixel, right? So in this case, we kind of get the idea or kind of conditional probability of this particular pixel or this particular pixel given the pixel value of this top left pixel value. Okay. So in this case, so if it is a black, and then so still we have a high probability of seeing another black pixel on the right or on the bottom, right? So that way we can kind of think of this conditional probability of this particular pixel value, right? Given, so suppose this one is maybe, so x, xi comma j. Yes, suppose this pixel is y and this pixel is x, and then we can kind of think of this conditional probability, okay? Observing the pixel value of this x position or this position being whether it's a black or maybe it is facial color, and then it will kind of influence the probability distribution of this pixel of this y position, okay? So this kind of intuition is reflected in this pixel RNN, okay? So we decide, or we first generate this kind of pixel, and then once it is a black, and then we still have a high chance of generating another black on these two pixels. But once we decide to generate this pixel as maybe facial color, and then maybe this pixel should have the similar kind of facial color, and this one also should have a kind of a similar color, okay? So those kind of conditional probability is modeled based on our LSTM model, okay? Okay. So although this is like following this 2D grid, but this is inherently or essentially the same as the sequence generation that we are already familiar with in the context of a text generation. Okay, so in the case of text generation, whether it is a machine translation or chatbots or maybe other kind of generative models or maybe image captioning and so on, and then we have an RNN cell, right? And then this is a given input, maybe start of sentence token. Okay, and then we have some hidden state vector, and then given these two information, okay, so that will work as kind of condition. Okay, so those information is like the pixel value, particular pixel value assigned to the previous time steps location, right? And then given those information as our condition to kind of specify our probability of generating the next pixel. Okay, so suppose this pixel is something like this, and then given some information, so this one is corresponding to this position. Okay, so once we generate it, our particular pixel value corresponding to this start position. Okay, and then we will just give it as a new condition or additional condition. So to generate maybe this pixel, okay? So in this case, we are given this hidden state vector coming from the previous time steps LSTM module as a hidden state or cell vector, and then this additional information of the particular pixel value that was assigned in the previous time step or the left pixel, okay? So this is essentially the same model, and then it is just nothing but a 2D extension of it. Okay, 2D extension of it. So here, when generating this particular pixel value at this position, And then what is the input value? So the input value is coming from those two positions, okay? And then those two pixel values will be just concatenated as a input in the next time step, okay? Okay, and then also this those two pixel positions will have their own RNN cells or LSTM cells that will generate their own hidden state vector, right? So those two hidden state vector coming from here will also be concatenated as a new hidden state vector, okay? So from here in our RNN cell, and then we generated maybe a 5-dimensional hidden state vector and the 5-dimensional hidden state vector, and then this cell will take the previous time steps hidden state vector as a 10-dimensional vector, and then it will be given as an input to this new cell at the current time step, okay? And then it will generate just a single 5-dimensional hidden state vector, okay? And then it will be propagated to the right and to the bottom, okay? Okay, and then how do we train this model? Okay, so now we understand how it works, right? In this kind of a sequential process of generating those pixels from the top left to the bottom right, right? And then how do we train that? The training process is, it's just the same as just the language model that we are already familiar with, okay? So in the case of language model, whether it's a character level, so in the case of character level language model, HELLO, for example, and then we have to generate ELLO and something like that, right? And then here, suppose we choose one particular image out of 100 different facial images, okay? So we chose one particular facial images, and then from here, we see the black pixel in that particular image, and then we just give it as an input, right? And then the next pixel, so we basically have all the pixel information in this given training example, right? And then we just train this model, right? So that we kind of generate or predict the next pixel values for our given training facial images, right? So this is how we train this pixel RNN stuff. Any questions so far? Okay, and then now you guys have studied like a conv sequence-to-sequence model, right? So basically, sequence-to-sequence model, I mean, the output was the sequence of the tokens or the keywords that we generate in the context of maybe natural language domain. So that is literally one example of the generative model. So just like we can, as we can replace the existing RNN-based generative model by using the convolution, right? So if you remember, and then kind of conv S to S will generate by just applying the convolution filter to generate the particular token, and then once it generates the next token, and then it will apply another conv filter to generate another token, right? So this RNN-based pixel generation can be replaced by this conv-based generation model, right? So let me ask the following issue. So what was the advantage of the CNN-based sequence generation compared to the RNN-based sequence generation? What was the advantage of using CNN in maybe sequence-to-sequence model? 네? 그렇죠. 네. Right? So RNN, so here, what is the input? I mean, the sequence-to-sequence is taking the input as a sequence, right? But here in this process, we don't have any input, right? So if you think of this kind of generative model, I mean, like a language model, whether it's a character level language model or word level language model, we will just need to have this start of sentence token, and then we can kind of maybe random vector as a kind of previous time steps hidden state information, and then it will just ignite, or it will just cause this model to generate any particular sequence of our characters or words, right? So that was kind of pure kind of a generation model, right? So this model is corresponding to that, right? So we don't have any given input sequence that we have to transform or convert, right? So in that case, if we think of like a sequence-to-sequence model when replacing this RNN or LSTM with the conv layers in a encoder and also in decoder, so we are thinking of, in this particular example, we think of like a convolution-based decoder model, right? So in that case, how did we train our kind of this decoder model or the language model in given this hello example? Okay, so in general, start of maybe sentence token should generate maybe H, for example, and then here given this particular character sequences, and then our input was like, so this whole sequence was given as an input, and then these were our output that we train, right? So this is how we train this character level language model, right? So in this case, if we think, if we apply this LSTMs, and then we have to generate the hidden state vector over here, and so that was the main kind of bottleneck or main cause of not being able to parallelize this process. But if we apply the conv model, right, and then the conv can be just applied to the given input sequence, right? So in this case, it can be parallelized, right? So that is the main advantage of using conv instead of an LSTM when training our model. But how about the testing or the inference time? So in the case of an inference, does this CNN-based decoder or a conv sequence to sequence, I mean, did it have such kind of a computational like advantage or efficiency? It didn't compared to LSTMs, because in the case of testing time, we don't have this previous time steps tokens that was generated. We have to generate each token one by one during the test phase, right? So related to this kind of training process, what was it called? That okay, so in the case of training example, suppose we generated maybe O instead of an L, and then why not giving this as an input to the next time step? We can do that, of course, right? So we have like two different options, right? Giving the the actually generated token at the previous time step, or whether it was correct or not, we can just give the correct ground truth token that should be generated at the previous time step. So that was called what? So it was called some forcing, right? So it was called a teacher forcing, right? So you have to prepare for all these for your exam in next Monday, right? So you have to know, all of them, within a week. I mean, if you didn't. Okay, so assuming we use these ground truth previously generated tokens, and then the training can be parallelized, but then during the test time, we have no previously generated tokens until we actually generate it. And so, even though we use the conv-based decoder model, during the test phase, it cannot be parallelized, right? So this CNN-based generator, will be faster during the training, but it's still slow during the test time. Any questions so far? Yeah, so in the case of this language model of generating those character level kind of RNN things, and so in the case of pixel levels, so pixel-wise CNN is working like this. So generating this pixel, and then we apply this particular window, right? And so like it's a 4, yeah, maybe 5, and then the 5, and then we are using like these 4 and 1, right? So it's a 5, and so we have 20 pixels over here, and then over here we have 2 pixels. So using 22 pixels and assigning a particular linear combination coefficient, okay, to generate this particular activation value, or I mean it can be designed as a multi-layer convolutional neural net, right? But if we think of just a one-layer convolutional neural net, and then the linear combination coefficient will be assigned to this particular windows and the pixels within that window, okay? And then that comb filter will be applied by using the same or the common linear combination coefficient by just applying like 1 pixel shifted version like this to predict this pixel and so on, right? Okay, so that is just a simple kind of extension or variant of like a LSTM based sequence generator by using this comb filter. Okay, wait, 네.
컨텍스트 사이즈가 5곱하기 5 돼 있으면
네.
오른쪽 아래에 2개 있는 빈칸을 보이잖아요.
네.
저 부분은 그냥 제로 펜지같이 똑같이 채워야 돼요.
아, 여기요? 이게 근데 이게 나도 정확한 디테일은 잘 모르고, 이게 그러니까 여기서 지금 이 필터 자체가 이런 모양 자체가 좀 이상하잖아요. 그래서 이거를 내 생각에는 그 임투 코린이 뭐 이런 거 써갖고, 네, 그러니까 필터가 좀 이런 이상한 모양으로 좀 정의가 되는 거예요. 네, 그러니까 꼭 사각형의 필터가 아닌 거죠. 왜냐면 이거는 여기 값도 없고 요 세 개가 하여튼 없는 거잖아요. 이렇게 좀 약간 빵꾸 떨어진 그런 거잖아요. 여기는 아직 우리가 제너레이터를 안 한 거니까. 네. 근데 사실 이걸 임투콜 같은 걸로 하면 이게 쭉쭉 펴지잖아요. 쭉쭉 원뒤로 쭉쭉 펴지니까 그때는 이제 문제가 없어지고요. 임투콜도 다 알죠? 그것도 시험에 나올 가능성이 높아요. 네, any other questions? Okay, so these are the pixel RNN and CNN's examples of generating those images. So it's just like a character level kind of language generation of generating maybe Shakespeare's like like poems and so on, right? So it's exactly the same in the image applications. Okay. So let's discuss about this variation autoencoder. So its theory or its theoretical background is quite deep. So I have no way to cover this, and also I don't have like a sufficient insights about this the literature about it. But I'm just gonna give you just some kind of intuitive understanding of this variation autoencoder, which seems to be kind of sufficient to understand many of the state-of-the-art like VAE-based generation models in the computer vision and also natural language processing. Okay, so it is basically an autoencoder. Okay, you guys know what the autoencoder is, right? So given 100 different facial images, for example, and then we just train our encoder or decoder model. Okay, so this is an original image, and this is the reconstructed image, for example, and our loss function is basically like this guy, right? For example, like this is a Frobenius norm, or like the sum of L1 or L2, like a pixel-wise, pixel value difference, right? So that is the main criteria of autoencoder. Right. So the main idea of this, the main task that should be achieved when training this autoencoder is like, so given this bottleneck part, okay, is this bottleneck part, it has much smaller number in terms of the number of values that we are given. For example, this is maybe 64 by 64 and maybe 3 channels. Okay, and then here in this at the end of our encoder, maybe it could be 8 by 8 and maybe 16 channels. So I hope, yeah, those the product of these numbers are smaller than these numbers. Okay, is it correct? 64. Okay, so it's certainly smaller than that. Okay, so the number of 64 by 3 is much larger than 8 by 8 by 16, for example. Okay, so we have to like compress these given information by using a smaller activation map, and then even so, we have to be able to generate the original image or reconstruct this image. So that was main idea of this autoencoder, right? And in that case, so this part should learn or should encode those meaningful information about like the difference of this different eyebrow shape, or the different eye color, or whether this person has a mustache, or maybe whether this person has a sunglasses or glasses, and so on, right? So those variations are existing. I mean, the main kind of information to store to properly the original input image for all the 100 images that we are given, right? So that's the main intuition of this autoencoder. And this variation autoencoder is, you can think of it as like a kind of a extended or variant of this existing or original autoencoder. Although this variational has a kind of a special meaning in the context of a probability theory, or in particular probabilistic generative model, this variational kind of method indicates a particular kind of literature, or the theoretical background, or particular type of theoretical kind of method. Okay, but I'm not going to cover that at all in this particular class, but if you're interested, so just before I forgetting, its spelling is quite difficult, but so from now on, I mean, those topics that we are studying, including this generative model and also variational autoencoder, so you cannot, you don't need to just rely entirely on this particular class taught by me. So there are so many and rich tutorials and video lectures that you can kind of study on your own. Okay, so this guy is the professor at probably at University of Waterloo or some other university in US or Canada, but this guy has a really like insightful kind of background, and giving a nice lecture about this variational autoencoder. So if you're interested, and then you can watch it. And also, so I think this guy, who is a researcher at the neighbor Kuocw, and so this guy has also a nice kind of Korean kind of tutorial about this autoencoder, and also this variational autoencoder. And also, as I mentioned, the theoretical kind of depth is quite really deep about this variational stuff. And so if you're interested, and then you have to study whole new kind of literature called probabilistic generative model. And so this guy, who is a professor at KAIST, he has some good materials, or online lectures. Online lectures about this advanced machine learning stuff, which is about this variational inference. Okay, so this guy, so that word variance is coming from this kind of literature. So I no longer have an internet connection. But yeah, so if you're interested, and then yeah, I strongly encourage you to study this. And also, okay, it's still alive. So this book, which is free for download, Elements of Statistical Learning, is also quite good and insightful book that you can study your own. And then also this PRML, which is also recently available for public use. And so yeah, you can study this book called this PRML, like pattern recognition and machine learning. So this book is really, really good. I mean, giving the good background and the literature about this probabilistic generative models. Okay, so back to the only the intuitive understanding or explanation about this variational autoencoder. So you understand this. You understand how it works for this autoencoder, right? And then this variational part is like this. So given this encoder output, I mean for this encoder output, this VAE or variational autoencoder is giving us two sets of this activation map. So the first one is like this guy, and then the second one is also having the same size of an activation map. Okay, so it generates these two sets of activation map, and then so if you remember, like gated linear units, gated linear units, and then it's basically the variant of a conv layer, and then it will also generate these two sets of activation map, right? And then for the second one, we just apply the sigmoid nonlinear unit in an element-wise manner, right? So that each value is ranging between 0 to 1, and then we just multiply it with the first one, right? So that's how this GLU or gated linear unit is designed, right? So where was it used? GLU? It was used as a main conv block in the 저렇게까지 얼굴을 가릴 필요 없었는데 거의 어디 검찰 출두하는 느낌. So it was used in the conv S to S, right? So conv S to S, this GLU was the main conv block, right? Okay, so this variational autoencoder, you can think of it just like that, but I mean, in a sense that it also generates these two sets of conv activation map that has their own different roles, right? But here the role of it is like the second one is used as a kind of a noise generator that will add to this conv block. Okay, so let's see. So in this case, I mean, we generated like two sets of activation values, where the first set is corresponding to the mean, and the second one is indicating the variance, right? And then using those two sets, we actually scale and shift the given activation value, right? So in this case, it's kind of similar. So let's just forget about conv, but let's think of this variational version of the fully connected layer. Okay, so suppose we have maybe 10-dimensional input, and then we want to generate 2-dimensional, maybe 3-dimensional output as our activation map. Okay, so in this case, suppose our activation map was 1, 3, 2, and then now, I mean, there were like another kind of another layer when discussing this gated linear unit. If you remember our lecture, and then I mentioned about this max out unit, right, which just generates two different sets of like activation map that we want, right? So it is kind of similar. So so we generate another three-dimensional output. So we basically two sets, right? And then suppose those three values are maybe 4 and 9 and 25, okay? And then those ones will work as a kind of a noise generator that will add to the original, the first set of output activation map. So here, this is how it works. So this one will be actually changed into this. So given this, so this one indicates the amount of noise. So so in detail, like this, in this case, we just generate one single sample from here. So it is like a mean value of 0 and then the variance of 4. Okay, so suppose we kind of generated a random sample of 3 or maybe -3, right? So we generated this random sample which is from the Gaussian distribution that has a 0 mean, but the variance is specified this value. Okay, and then we just add this one to the first activation map. Okay, so this value will be transformed or converted into -2. Okay, so in the case of GLU, right, gated linear units, and then this one will go through the sigmoid, and then once we pass through the sigmoid, and then suppose the output was 0.85, and then this guy will be multiplied with this value. So this is how this GLU works. But this, in the case of this VAE, we just obtain the linear layer output, and then we just use it as a kind of variance value in this zero-centered Gaussian distribution. And then once obtaining a single sample, random sample from here, and then we add it to the original activation value. We do the same thing on the second and the third dimension. So in the case of second dimension, the corresponding Gaussian will be like this, right? So in general, if we obtain the random sample, and then that random sample will have a larger kind of absolute value than this, right? And suppose that value was 5, and then we will just add it to this 3, so that 3 plus 5 becomes 8. Okay. Okay, so this is how we kind of perturb or add the noise to our original activation map that we obtain. Okay. 이거 맥스아웃이요? 맥스아웃이 이제 GLU 이제 설명할 때 이제 그 맥스아웃이 이제 이 세 개가 있으면 이렇게 두 세트를 뽑아서 이 둘 중에서 맥스 오퍼레이션을 해갖고 이제 여기서는 이제 1과 4 중에 맥스 뽑고 3과 9 중에 맥스 뽑고 2와 5 중에 맥스 뽑는 거였죠. 네. 그래서 이제 그 맥스아웃에서도 일단은 기본적으로 뭔가 이제 두 세트를 생성을 해갖고 그 두 세트를 어떤 형태로 조합을 해서 이제 최종적인 우리가 원하는 숫자만큼의 그 한 세트의 아웃풋을 뽑는다라는 거였고, 뭐 큰 틀에서는 뭐 각각 이 디테일한 프로세스는 다르지만 이제 뭔가 하여튼 두 세트를 뽑아서 그 두 세트를 어떤 형태로 조합을 해서 이제 우리가 원하는 한 세트를 만들어 준다. 네. Any other questions?
교수님,
네.
지금
이 모델도 그 그레디언트가 전달이 돼야 될 거잖아요.
네.
그래서 인코더한테도 그레디언트가 가야 될 것 같은데
네.
저기 그 중간 베리에이션 과정에서 그 에스티메이션이랑 샘플링 과정이 들어가는데 저기서는 그레디언트가 어떻게
네. 그게 이슈예요. 네. 그 미리 알았던 건 아니죠. Okay, so in this process, so there is a kind of some transformation of some particular issue. So that issue is coming from this random sampling. Okay, so okay, up to this point, it is certainly differentiable, and then the next step was, the bottom part is the problematic part. So from here, we specified this zero-centered Gaussian distribution, and then specify the variance as our activation value, corresponding to this value, right? And then we obtained this random sample of -3, right? And then in this case, this part of obtaining the random sample from here to here, okay? So this part is not differentiable, right? So if you imagine, if you really try to differentiate this kind of process, so we are given a particular probability density function or distribution function, and then we randomly obtain the one sample from that distribution, and then how do we do the backpropagation? So it is not possible. So we kind of do the some trick called reparameterization trick. Okay, so that is really an interesting trick. So in this explanation, in this way of explanation, so this is kind of a partially differentiable version, but the way I describe this process is like half correct. I mean, the original process is like this. So the original process is, so when I explained this, I mentioned it as, or I explained it as, so this is the original value, okay? And then we generate the noise, and then we add it to the original value, right? But in the original process of this variational autoencoder, what we do is to, we consider this value as the mean value, and this value as the variance. And so our mean is 1 and the variance is like this, and then we obtain the random sample over here, okay? And then the second distribution that we obtain the random sample from is like 3,9, and the next one is like 2,25. So in this case, obtaining the random sample from these distributions, okay? So this part is not differentiable, but we have to do the backpropagation through those two parameters of this mean and the variance, right? I mean, that way we can backpropagate through this process, through this part, right? Okay, so to handle this issue, we apply this something called the reparameterization trick. Okay, so let's just ignore this part for now. So here we have an encoder, and if we have an image, and then we have two sets of activation values, where the first set will work as a mean and the variance. Okay, and then we random sample from those distributions, and then we will do some decoder for our rest of the process of this autoencoder part, right? And then we apply this reconstruction loss, right? Minimizing the difference of the given image and the reconstructed image, right? But when doing the backpropagation, this red part is not differentiable one, right? So this reparameterization trick is really like clever but really simple trick. So we still ignore this part. I will explain it shortly. So here, in this case, if you see the difference between this version and this version, okay? So in the case of the first version, at least we can do the backpropagation onto this value, right? Because, okay, so it is 1 plus negative 3, right? And then we obtain the negative 2 as the final encoding output, and then that will be used as an input to our decoder. And then we will obtain some gradient value corresponding to this output, right? And then what will be the corresponding gradient value when backpropagating through each of them? So this dy is just this is just an add gate, right? So this dy will be just duplicated into each of these two nodes, right? And so at least we can have, we have no problem of backpropagating through this activation node, and then we at least can train this half of our network, right? Okay, and then we also can do the backpropagation up to this point. But the problem is, from the the gradient value of this guy and like this guy of 4, right? That will be used to specify the variance, right? So we have no way to backpropagate through that value, right? Because this part was through the random sampling, right? So that part is like a separate part. That make it impossible to do the backpropagation, right? But let's think of this kind of process, okay? This kind of process of just specifying the normal distribution, of having the mean and the variance, like these two, by using these two activation value, and then I obtain the random sample over here, and then suppose this guy is -2, for example, and then this, suppose we have a gradient value of dy, and then can we backpropagate through these two? We cannot, because we have this, and then from here we do the random sampling to obtain this, or -2, and then we cannot backpropagate this random sampling to get inside to gradient to obtain the gradient corresponding to these two values, right? Because that is wrapped inside of our probability distribution as their parameter. Okay, so they are kept inside of those probability distribution that we sample from. Okay, so this is the trick. So at least from these two versions, you know that there's a second version has no way to do the backpropagation to either of these two values at all, but at least in this particular case, okay, so we can do the backpropagation at least to the first value, right? So that way, our mean and the variance, we can just get them out of the parameter place to specify our distribution. So that is the main idea of this reparameterization trick. So this is how it works. So the random noise to add to each of these three-dimensional activation value is always sampled from this Gaussian distribution having a zero mean and a unit variance. Okay, so it can be viewed as 1. Okay, so you always obtain those random sample from this particular distribution. Okay, and then suppose that value was point A, for example, and then this guy is what, 132 and 4925, 132 and 4925. Okay, so once we obtain this random sample to add as a noise to add to the first dimension, and then our activation map is like 1 plus 0.8 times, maybe 2, okay, square root 4, okay, and then let's see, the second one is 3 plus, for the random sample, the second random sample we obtained maybe -1.2, and then negative 1.2 times, for example, 9. Okay. So in this case, the random sample was obtained from here, and then distribution didn't have any activation or hidden state value that we generated inside of these parameters for this distribution, and all these activation values are now outside, right? Outside. And then suppose this guy is our activation map, 2.6, and then suppose we have this dy arrived at this particular node, and then we have no way to backpropagate through this, right? So what is the corresponding backpropagation value or the gradient value corresponding to these nodes? Yeah, dy will be just duplicated, right? Because this is an add gate, right? And then what about the backpropagate, I mean the gradient corresponding to our variance value. So this, yeah. So in this case, at least root of this activation value and their gradient value will be like, yeah, so dy times 0.8, right? So that will be the gradient for this guy, right? So in this case, we can now backpropagate our gradient signal through both of our mean and the variance term. So this is called a reparameterization trick. So what is the meaning of this reparameterization trick? So the reparameterization trick is like, so yeah, in this case, we want to obtain the sample from like this distribution, but instead of using this, we reparameterize this distribution as always like this guy, okay? And then once obtaining it, and then we just scale and shifting it, okay, to obtain the equivalent random sample just from like, yeah, just like this, okay? Any questions so far? Okay, so what's the intuitive role or effect of adding this kind of noise through this variance term that we have? So from here, okay, so yeah, intuitively you can just think of this 132 as the original activation value before adding some noise or before perturbing this original kind of encoding output. Okay, so once we just forward propagate that activation value through our decoder network, that will be just the same as the original autoencoder. But in the case of variation autoencoder, we just perturb this original signal, right? Okay, so in this case, you can think of this autoencoder as like, so we have some encoder-decoder model, and then we just perturb this encoder output by adding some noise, for example, right? But even in that situation, our encoder-decoder or this autoencoder's architecture should be able to generate this part, yeah, the original input image, right? So in this sense, it is, yeah, it can be viewed as, yeah, it can be viewed as a particular variant of like denoising autoencoder. Okay, so what was the denoising autoencoder? So in the case of denoising autoencoder, yeah, original autoencoder will just take the input as the original input image, right? Original input image. But what is the input to this denoising autoencoder? Okay, so this is the input to the denoising autoencoder and the output. Okay, so this guy. So we initially have this original input image, right? And then at each pixel, we inject some random noise, right? And then we will obtain this, right? So it's a perturbed version of our input, right? But even when this noisy or kind of a perturbed input information, we should be able to generate or reconstruct its original digit as this clean form, in this clean form, right? So intuitively, this denoising autoencoder is training our autoencoder in a kind of a more difficult or kind of a tougher situation, right? So we just hurt or we just perturb the original input, and even in that case, our autoencoder or our network should be able to reconstruct, the original input before adding any noise, right? So it should find out those hidden values, okay? Hidden values even after those input values are perturbed with some noise, right? And the main intuition is like, so if we know that this image is representing some digit, okay, and then it will look like 2 among maybe 0 through 9 of these digits, right? So in that case, if we ourselves as a human, if we have to reconstruct this image as an original input before adding any noise, and then we will have no problem. Almost have no problem of guessing or estimating or predicting this original input image is like this, right? So this is the denoising autoencoder setting that trains our autoencoder much harder, and that autoencoder can be used to perform this in-painting part. So this is also another kind of perturbation of our input image, right? So this guy is our perturbed version of our input image. So this is the original input. Oops. Oops. Okay, and then this is the reconstructed output. Although it is not perfect, but our network has properly learned that we have to fill those pixels that looks like a nose, okay, as a part of our facial image. Okay, so from that perspective of a denoising autoencoder that trains our autoencoder in a much difficult settings. So in this case, it is almost viewed as an autoencoder. Denoising autoencoder, where we add the noise not at the input layer, but at this particular layer. Okay. And even in that case, our denoising autoencoder or this variational autoencoder should be able to generate the original image. Okay. And also another interesting part in this variational autoencoder is so in the case of a denoising autoencoder, so this is a kind of a special case, but like in this case. So how we inject or how we add the noise to the original image is as follows. So we just add the random noise generated from the same Gaussian distribution of having 0 mean and maybe the variance of maybe 5. And this is kind of a hyperparameter. So once we set it as 5 as a variance or the standard deviation of our random noise, basically telling us the average amount of the noise, right? So if it is having a really small variance, and then it means that the random sample obtained from the distribution having the small variance, and then it will be close to 0, and thus we are adding really small noise. But if we have a large variance of our distribution, and then if we sample from that distribution, and then the values will have relatively large values on average, and then it means that we are adding large amount of noise, right? But the the key point is that when doing this denoising autoencoder that adds the noise to the input pixel level to the input image, and then all the noise are sampled from the same distribution of having the same variance, right? So in that case, yeah, we are roughly adding the same amount of noise for every different pixel position, right? But in the case of a variational autoencoder, so the main difference is that we add the noise to the particular layer of this encoder output, and also the amount of noise is actually determined by our network, right? Because those 4, 9, 25, so those values are determined or output of our network, right? And so if our network is thinks that this value should be really kept as it is without adding too much of a noise. So in that case, it really be a problem to reconstruct the original image. And if our network thinks that way, and then it will generate this the variance or the amount of noise value to be really small. But okay, if this value, even if it's a current, even though it is a currently 2, but this value, even if they are perturbed with a kind of large amount of noise, okay, and then if it thinks that our network thinks that it has no problem of reconstructing the original information, even with the relatively large amount of noise, and then it will generate large value over here, right? So yeah, this is another interesting aspect of this variational autoencoder to determine the amount of noise by our network itself. Any questions so far? Okay, and then how do we utilize, or how do we use this variational autoencoder for our generative model? So in the case of generative model, we should be able to generate the particular image from scratch, right? Given no input at all, we should be able to generate a particular image. And then how can we utilize this variational autoencoder for that purpose? So this is based on this kind of regularization that I ignored previously. So the main idea is like this. So given each of our image, and then it will determine its activation value that will work as the mean value and also the variance value, right? And in this case, for the first image, out of 100 facial images that we have, it will have its own mean and the variance value, right? And then also another image, or the second image, will have their own mean and the variance value, right? And then suppose like let's think of this guy is the mean value for the second image, okay? And then on average, if we have only the 2 images in our training data, and then what will be, from the probabilistic sense, what will be the global average? Global average. So in general, given one image, the mean value of the first activation is 1, and then given the second image, the mean value will be 4, right? But if we have no images at all, what will be, given no information at all, what will be the corresponding mean value? And then the mean value will be roughly like 1 plus 4 divided by 2, right? So it's like 2.5, right? So let's think of this given image as our condition to specify our distribution, for the first activation in terms of its mean and the variance. Okay, so in this case, suppose given the two images in total, and then the first activation value has the conditional mean value of 1 and 4, and then roughly given no information at all, our marginal distribution where there is no image given, and then the global mean value can be considered as 2.5. So in this case, I mean, in this case, without loss of any kind of, I mean, in this guy has no problem of shifting these two values as maybe this guy as negative 1.5 and this guy as 1.5. So just those centering those two values, right? So out of 100 images, okay, so we just make the overall mean of those means given each of our particular image. Okay. So yeah, let me have maybe up to 5 minutes to finish this VAE. Okay, so in this case, yeah, having this mean as these two values or 1 and the 4, I mean, it is just an equivalent, because in the next layer of our conv or deconv, or maybe another fully connected layer, just to following this layer, and then it can also just change those values by using the bias, right? So compared to this case, if we use the bias as a kind of a larger by 2 compared to this case, and then we can have no problem of adjusting them, right? So in this encoder output, we can kind of regularize, or we can just make the global mean of every dimension as having 0 mean and also the univariance. So for example, if this has the variance of 4, and maybe the second one, I mean for the second image, and then it has a 4 and the variance of maybe 16, okay, and then we can just scale it down, okay, we can just scale it down, and then it has no problem of handling this different scales in the next layer. And so so the main idea here is that roughly when given each of our training images, and then the output from so from this from these particular like normal distribution, okay, so given 100 different images, and then we will have 100 different normal distribution and their own mean and the variance value, right? And then overall their mean, I mean mean of this mean as 0, and the overall mean of these variance as 1. Okay, so altogether, when given each of our 100 images, and then if we just draw those points corresponding to each of conditional distributions, and then overall their marginal distribution should be having the 0 mean and the univariance. And so it's just like this. Okay, so I mean, I hope it helps. So in this case, suppose we have like 2-dimensional outputs at the end of our variational autoencoder, okay, or the activation map of the result of this encoder output, right? And then each point you can think of each point as a particular image that we have, right? And then its its mean and the variance value. Okay. So in this case, if we have 10 different classes, okay, 10 different classes, like mnist digit images, and then the first digit of maybe 0, okay, and then 0 may have, 0 have like 50 different samples, and then their corresponding like mean value and the variance value will have like this value has the mean value over here and the variance like this, and then this guy has this, and this guy has this, and so all these green values are corresponding to the digit of 1, and this guy is digit of maybe 2 and maybe 3 and so on. But on average, considering all the data that we have, and then it has like this 0 centered, having the 0 mean overall, and then although it's like it doesn't seem to have a unit variance, but the variance should be kept as close as 1. Okay, so that is another kind of constraint. Okay, so so what's the role or effect of having this like regularization of the overall distribution, so that the overall distribution have a 0 mean and the unit variance? So in that case, we can actually utilize that by just throwing away this kind of encoder part and use this generator to purely generate the images that we want to generate. So in this case, what will be, given a particular image, okay, when encoding it through our encoder, and then it will create the particular mean and the variance value. But what if we don't have any images at all from the beginning? Okay, and in that case, we can just expect the mean as 0 and the variance as 1, right? So from this standard or kind of default or the marginal distribution, we can just generate kind of random sample from that, and then we use it as an input to the decoder, and then it will generate a random image that will follow our follow distribution of the real images. Okay, so that is the role of this kind of regularization, so that each of our generated mean and the variance should be close to the mean of 0 and the variance of 1. Okay, so we kind of impose this kind of regularization so that the overall center is placed at the origin, or 0, 0. So that is the autoencoder, and how we use it to pure generation. So these are outputs, and then we didn't even cover again, but the time's up. So okay, so that's it for today, and then probably I'll ask you guys to watch some of the videos about this again. Okay, thank you very much. And next class we will have a presentation session for your projects. Okay, thank you.